Welcome. We will continue 2 to the power k factorial design. So far, we have seen 2 to the power 2 design, 2 to the power 3 design and general 2 to the power k design with n replicates or with n replications. So, in this lecture, we will see what will happen to 2 to the power k factorial design when n equal to 1. Otherwise, we say today's lecture is 2 to the power k factorial design with single replicate. So, topic is 2 to the power k factorial design with single replicate. Now, what are the things we will discuss? We will discuss in detail how do you conduct the analysis when you have single replicate in 2 to the power k factorial design with an example. This lecture also prepared based on chapter 6 of Montgomery, design and analysis of experiments. Let us see some of the issues related to your experimental design and the prediction of response line or response surface when the number of replication is less. So, we will go for less replication or single replication owing to the resources or otherwise limited resources. So, that means if you have limited batches of raw material, in that case what will happen? You cannot conduct full replications, n replications, you may require to conduct one replication per batch for a particular combination like this 2 to the power k. So, what I mean to say, you have resource crunch, whatever may be the reasons. So, now if you do that, what will happen? That the effect of noise that will be there and that effect cannot be separated out ultimately, and the estimate because of the replication n is 1, the error estimation will become incomplete or it is difficult or it may not be able to complete the error, you will not be able to do this. That is the true factor effect which is inclined slightly this one, and this may be the bound 95% bound. So, if you have less number of observations like single replicate case, you may get a predicted or fitted line like this. So, in this case what happened? It is deviating from the true factor effect line. That means, if your factor, if a factor you keep at minus or low level, so the true effect is here, and when you make it high level, the true effect is the difference is there, but because of less number of observations, if you get like this over here, it is showing almost no effect on y. So, this is due to random variability in y. Two measured responses are obtained shown by dark dots, estimated factor effect is close to 0. Now, if you have more number of observations, what happen? This estimated effect line, this will become closer to the true effect. So, here what happen? Your due to the less noise, less variability in y, gap between low and high level of factors is more and reasonable estimate of the true factor effect. Okay. So, in a nutshell, what I mean to say, if n equal to n, your estimate will be more precise. and it will be suppose if this is the true effect, it may be close to that, low to high. This is y and this is x. If n is 1, what will happen? You may find that the same case that may be like this. So, there is no effect, that is not the true sense. Okay. So, be careful that the replication is a issue, very key important issue. So, it is always advisable that you go for more replications, but many a times you cannot do this. So, here what we are showing you, that if this is the situation, how can you analyze the experimental data and find out that what are the effects that are significant and what are the effects that can be excluded from the model. Okay. So, a single replicate of a 2 to the power k design is sometimes called an unreplicated factorial. Due to single replicate, no internal error is estimated. Higher order interactions are assumed to be negligible. Most of the systems are dominated by main effects and low order interaction, whereas higher order effect interactions are negligible. This is called the sparsity of effect principle. So, now question is that why single replication will work? This will work because of the sparsity of effect principle. Suppose you have A, B, C and D, that 4 factors, each at 2 levels. So, 2 to the power 4 equal to you have 16 runs, or 16 runs means 16 treatment combination, let it be treatment combination. Now, if you have every treatment combination having 1 replicate, so you have 16 observations, and you know that what are the number of parameters to be estimated? 4 main effect you have to estimate, 4 C2 2-way interaction effect, 4 C3 3-way interaction effect, 4 C4 4-way interaction effects. These are the effects you have to estimate. So, what is 4 C2? 4 into 3 by 2, that means 6, 4 C3 also 6, 4 C4 is 1 and this is 4. So, how many you require? 6 plus 6, 4 C3 is 4 factorial 4, this is 4. So, you require to estimate 15 effects, correct. Now, if your n equal capital N total is 16, so for total computation of SST, total SST, that you have 15 degrees of freedom. Now, you require 1 degree of freedom for each of the effect parameters. So, this 15 degrees of freedom will be lost, because 1 for 4 degree will be lost for main effect, 6 and another 6 plus 4 11 for the interaction effects. For error, there is no degrees of freedom available, means no free observations available which help you to estimate the error. So, this is what is the problem you will be facing when you have single replicates. Then what is the way out? Way out is that the sparsity of effect principle, sparsity of effect principle. What does it mean? Main effect usually becomes significant, maybe 2 interaction effect will also may be significant, but 3 interaction effect, 4 interaction effect, then that may be insignificant. So, that means you do not require to compute all the parameters, effect parameters. 4 plus 6, maybe you will estimate 10, then remaining this 5 you do not require to estimate. In that case, what happens, these 5 degrees of freedom, they will go to error estimation. So, that means we will be in a position to check whether these effects are significant or not. By saying this, I am not saying that all the 2-way interaction will be significant or all the main effect will be significant. The effectivity of percept principle says that The higher order interactions usually contribute less compared to the lower order interactions. Okay. We will see all those things with reference to an example, and by this time I am assuming that you all know that what is contrast, and you know what how to compute the effects equal to contrast by 2 to the power k minus 1 into n. Here n is 1. So, C by 2 to the power k minus 1. So, then your SS C square by 2 to the power k into n equal to 1. So, that is C square by 2 to the power k like this, and also you know degree of freedom, you know what is ANOVA table and how to estimate your F0, all those things that is known to you, and we have deliberated all those things in say almost all the lectures, what is ANOVA, what is degree of freedom, what is F0. So, I am sure that you will not face any problem related to this test hypothesis testing. Please keep in mind, in all the lectures so far, start bearing a few in the beginning. So, we are always doing some kind of hypothesis testing all the classes. So, here our in all those this later lectures, we are talking about main effect and interaction effects. So, there will be hypothesis related to each of the main effects, related to each of the interaction effects, and using F statistics you are basically finding out whether the effects are significant or not, and the basis is that partition the total sum square into the effect sum square, and then use mean square, sum square, and then do the traditional way of analyzing these things using ANOVA. So, here what I will show you, this is example that 4 controllable factors are there, that means A, B, C and D, each at 2 levels. Due to shortage of raw materials, only single replicate is possible to run, and compute effect, you require to compute effect of A, B, C, D, A, B, B, C, all those effects. So, we have seen that there will be 15 effect parameters, and then compute sum square for each of the effects, 15 effects including sum square error, and do test for significance, comment on the error and effect estimation. So, I have already given you enough hints on the error calculation and effect estimation. Let the data is like this. Okay. So, this example is available in Montgomery book. So, so far I am assuming now that you know why this is within bracket 1, this is A, this is B, this is AB. So, if you scan through each of the rows for the factors, so if you find out find out a row which contains all minus 1, that is within bracket 1. So, A means the only the effect that the column of factor A and row 2, you see that this is 1 and all others are minus 1. So, A, that means the A at low and others are like the same manner. When A, B, C, D you are writing, you see all are positive, plus 1, plus 1, plus 1. What is the response here? Response 44 means the y value here. Here what we are saying, if you conduct an experiment keeping A, B, C, D all at low level, the response value is 44. Suppose what is 100 here? Here this is AD, that means you are keeping A at high level and D at high level, and both B and C at low level, and then if you run the experiment, you will be getting the response value 100. Similarly, here A, B, C, D 94, it simply indicates that when all the factors are at high level, the experimental result with reference to the response variable values is 94. That is what you got. Okay. So, now if there would have been more replications, you would have more number of response values here, maybe 44, maybe for 50 or something like this, but we have only single replicate. So, that is why these are all single observed values when you have conducted experiments against each of the experimental settings. Okay. Now, this is what is again your design matrix. What is your design matrix here? You have 1, 2 like 16 runs and you have A. So, it will be -1 +1 -1 +1 like this, and then B, this will be minus plus plus like this, then C and D. So, this is your design matrix. So, from this design matrix you can, using the algebraic signs what we have discussed earlier. So, you can find out this design matrix also. So, you have A, then you have B, then you find out AB. You write C, then you find out AC, you find out BC, then you find out ABC, then you put D, you find out AD, you find out BD, you find out CD, then here ABC, then AB, similarly you will be getting ABD, BCD, ACD, ABCD. So, like this. So, that is what is written here. So, if I am missing something, you can fill up. What happened in the previous slide? ABCD, the column you got, and here AB, AC, BC, ABC. So, what is AB, AC, BC? That multiplying A column, B column, you get this, multiplying A column, C column, you get this, like this. So, this entirety is known as the, basically the, what I am saying, the total design including the interactions. Okay. So, this is then what happened when you have conducted experiment and we set the labels like this, these are the values. Okay. Now, what we want basically, we want to compute the contrast and then we want to compute the contrast square, because contrast will give us the main effect, all effects, and contrast square will give us sum square. So, what we have done, suppose you want the contrast for A, then the eighth column will be multiplied by this run level, the treatment combination. Here this one will, this numerical value will be getting from this total. So, this total multiplied by A, then you are getting this column, total multiplied by B column, you are getting this column, this column, this column, like this. Okay. So, how are you getting this column? You are multiplying this A column with this total column. Then when you take the sum, you are getting contrast, because when you multiply this run column with this A column, factor A column by the run column or treatment column, you will get contrast, because this will be just adding or subtracting things. So, now using the total value, that value of each of the treatment for Y, you will be getting here also the numerical values. Now, when you take sum of all those numerical values, you are getting 165. This 165 is the contrast for A. Similarly, contrast for B, contrast for C, contrast for D, and their squares are like this. So, you do by your own. If there is some kind of computational mistakes, maybe while doing all those things in Excel, if we have committed any mistake somewhere, please rectify. And but this is what is the procedure. The more important thing is that we are giving you the procedure how you will be doing it. Okay. If there are some error somewhere in calculation, it is always correctable. So, that means A, B, C, D contrast you have computed, contrast square computed. Similarly, A, B all second order interaction, third order interaction and fourth order interaction, you have found out the contrast and contrast square. So, once you have the contrast, you know now what is the effect and sum square. So, we have found out effect accordingly. Okay. So, I will show you the last one. Suppose ABCD effect, how it will be effect ABCD, how it will be calculated? ABCD will be contrast ABCD divided by what happened, to the power k minus 1 into n. Now, what is contrast ABCD? You see that this is what is the ABCD column. Now, contrast ABCD is 13, sum of all those values. So, that means this one is 13. What is your k? K is your 4. 4 minus 1, that will be 3, and n equal to 1. So, that means 13 divided by 2 to the power 3, that is 8. So, your 8, this value is 1.625. Okay. So, as a result, you see here what is happening here, ABCD is 1.625. Suppose this is what is the effect calculation, ABCD effect. Suppose you want to compute sum square ABCD, what you will write down? C square ABCD divided by 2 to the power k into n. So, C square is 13 square divided by 2 to the power 4 into 1. So, this is 169 by 32. Is it so? 16. It will be 16, 2 to the power 4 is 16. So, then this will be 10.56. So, see here that SS is 10.56. So, how many parameters you have to estimate here? There are 15 effect parameters, 4 main effects, 1, 2, 3, 4, 5, 6 two-way interaction effects, 1, 2, 3, 4, 4 three-way interaction effects, and 1 four-way interaction effects. And their effect estimate effect is contrast by the 2 to the power k minus 1 into n. That sense you are able to find out all the effects. You see the effect values are positive and negative also. That means some of the effect when goes from one level to another, low level to high, the y values are increasing, some cases it is decreasing, and that is true for interaction effects also. And then SS also you are computing in the same manner. So, what will happen to the total? Total you can compute, but what will happen to error here? You cannot find out error because you do not have free observations for you to compute error. So, as a result, there are two way things that you stop here, or you find out some innovative way so that you can compute the errors. So, the innovative way is that you know the SS already. This SS is basically the explanation, because we all know from the analysis of variance that sum square total is the sum square error A, sum square B, sum square C plus sum square D plus sum square AB plus sum square BC plus sum square AC plus sum square AD plus sum square BD plus sum square CD plus sum square ABC plus sum square your ABD plus sum square ACD plus sum square BCD plus sum square ABCD. So, this total is sum of all the individual contribution. So, as a result, it is advisable that find out the percentage contribution of each of the effects. So, this is nothing but what way you will find out the percentage contribution, that individual contribution divided by total contribution. So, this is what is the contribution of A to SST is 30.66%, this divided by SST. Similarly, contribution B is 0.82% only, contribution C is 7.75%, contribution D is 14.89%, like this. Okay. So, that means you are getting each of the contribution. Now, here what happened, you have to drop some of the parameters in order to get the error. as we say that the higher order interactions will be dropped, or so in that case what is happening, there is issue that suppose A is significant, B is significant, then its second order interaction A B, it is better to keep that in the model, because if you do not consider that interaction, what will happen, your result may be erroneous. So, as a result, from this contribution plot, you find out which are the effect parameters whose contribution is negligible, but whose lower order contributions are not there. Considering this, we found out that B is negligible, and we found out that BC, BD, ABC, ABD and your BCD, ABCD all are very negligible. But in the same logic, why we should not keep this one, that CD, because this is also negligible. Similarly, ACD, this is also negligible, because percentage contribution is less than even 1. But you will not do this. The reason is, here A is significant, C is significantly contributing, as well as D is also significantly contributing. So, that is why their interaction AC, let it be there. So, similarly interaction ACD, let it be there. So, in a nutshell, what we are saying, that we are saying that you find out the main effect part first, those are which are contributing, keep them, then see the interaction part A, B, B, C like this, and then see that which are contributing, in the sense the percentage contribution is reasonably high, but it is a subjective one at this level. So, then B, A, B, B, C, C, D, A, D, A, D like this. So, here you find out which are contributing, those contributing keep, but it is something the contribution is low, but its both the primary main effects are still significant, then that also you keep. So, in that sense we have gone. It is always advisable that higher order interaction should be dropped, provided there will be significant evidence that if you drop them, you will not finally landed into a wrong model. The approach is, first find out the effects, main effects, drop which is not significant, and then subsequently find out the second order effect and drop which are not significant. But at the same time, if you see that you are dropping a interaction, second order interaction whose primary or main effects are significant, advisable that you do not drop this, keep in the model. Okay, by following this logic, what happened? We have dropped 8 effect parameters: B, AB, BC, BD, ABC, ABD, BCD and ABCD. So, then we have a new table where we are saying the sources of variations are A, C, B, D, AC, AD, CD and ACD, and the rest of the effects, the 8 effects what are dropped, they are basically comprising the error with 8 degrees of freedom. Okay. So, this is our final ANOVA table. Now, you are in a position to find out MS for everything, also you will be in a position to estimate the F0, because you have error MSE is also available with you. So, as a result, if I follow this one, the F0 value, you find out that A, C, D, AC, AD, they are significant and others are not significant. Okay. Now, we refer, then you can compute the tabulated value, and this is what you are getting. Okay. So, this is what is the logic we have provided to you, but there is no sacrosanct, it is not sacrosanct that you have to follow only this logic, there will not be alternative way of thinking. But whatever you do, you must keep in mind that the basic objectives of this kind of experiment is to finding or screening out the insignificant factors and their interaction or in their interaction effects, so that you will get a good model and keep the meaningful factors for further analysis. So, now if we consider that these are the factors which are basically to be kept in the model, then you can go for the regression analysis and you will find out x 1, x 3, x 4, x 1, x 2, x 3 and x 1, x 4. So, A will be denoted by x 1, C x 3, D x 4, x 1 x 3, x 1 x 4. This is what we have considered here. So, x 1, x 3, x 4, x 1, x 3 and x 1, x 4 considered here. So, and then these are the different run level, this is intercept, and this is using Excel sheet we found out the error quantity. Okay. Why error is important? Because you have to do residual analysis, and that residual analysis will tell you whether the model is fit or not, whether the assumptions are violated or not. Also, from regression point of view, you can find out the R square values and other things. Okay. So, this response surface gives us this kind of contour plot. So, I will explain only one. Suppose if you develop contour plot for x 1 and x 4 keeping x 3 constant, then what will happen? You will get this kind of plot. So, what is needed here in addition to this, that what is the y value for this line, y value for this line, y value for this line. So, here what happened, they are almost parallel. So, that means the interaction effects are not that interaction effects. If you see AD, they are significant, AD, AC significant, but anyhow because this is AC means x 3 and AD is x 4. So, in this plot we are talking about x 1 and x 4. Okay, keeping other x 3 at constant. But anyhow, when because of interactions, if we judiciously find if we go for other options, we may find a curvature some kind of curvilinear plot also. What I mean to say, suppose you are doing this, it is this kind of plots represent that there is no that interaction term like beta 1 2, these are not there. But in this case from the data we got this kind of things, but many times you may get like this kind of plot also you will get. That is what is when the interaction effects are significant. So, here in the last plot is the normal probability plot. So, the residual vis-a-vis cumulative probability, when we plot, we found out that this is basically using Excel we plot, but it is better to use the probability paper. So, in that case what you will get? You will get a straight line. When you join the points, you will get a straight line. If you get so, then that is what is your that errors are normally distributed, and that is one of the assumptions. So, another major you can do what we have already discussed several times, the fitted value versus residual. Suppose this side residuals and this side the fitted y, that is y cap. So, here it is expected that you will get random observations, random plot. It should not be any trend or anything like this. This is one for constant variance, this is required. One is normality, another one is maybe the order of experiment vis-a-vis this side is the error values. So, that also should be random, it should not show any pattern. So, that means the autocorrelation is not present, that is to be tested also. So, okay, all those tests we have discussed earlier in different cases, but please remember this is also valid for this kind of design. So, here again let me tell you that we have used the content of this book, Design Analysis of Experiments, written by D.C. Montgomery, published by Wiley. Thank you very much. I hope you have understood the 2 to the power factorial design when there will be many replications and when there will be single replication. In case of single replication, we have given you a scheme that how to compute the errors even though you have single replicate, and using the effect of sparsity of effect principle. Okay. Thanks a lot. Thank you.